Hello, welcome to Materials and Me. Materials being the study of stuff and me being eerie. If you're like me and you've ever gone down, the rabbit hole of study tube, you'd have heard all these evidence-based methods for you to study smart and not study hard. And one of the ones I've actually come across most recently is something called priming. And you're like, oh gosh, Sherry, what the heck is priming? Wait, calm down. I'll tell you. Like, there's this content creator called Janu. And I like the way he describes this. He sort of describes it using like a Lego analogy. So imagine you buy a Lego set. Obviously, there's a bunch of pieces, there's instructions, but before you start putting anything together, you first need to look at what it is you're actually trying to make. So, like the picture on the box is what you look at to get a rough idea of what you need to do. And when you prime before you study or you go to a class, that's basically what it does. Before you go into depth, priming just gives you the big picture. And I remember, like, when he explained it, I was like, oh my gosh, like, that makes so much sense, like, to do that first. And so, finding out about priming, I was like, oh my gosh, like, I really wish I found out about this sooner. And one of the things that I would have used it for definitely is crystallography. This video basically is what I wish I had, just to try my best to give the big picture behind what crystallography is. So yeah, let's get into it. First and foremost, the what. What is crystallography? And the long and short of it is crystallography basically is the field of science that allows you to understand the way atoms are arranged in a structure, particularly a crystal structure. Okay, so the why. Why is it important? You can have two completely different things made up of the same element, but like what distinguishes them is their structure. And the difference in the way the atoms are arranged in diamond and the atoms are arranged in graphite is what explains why they behave the way they do, why diamond is one of the strongest materials in the world, and why graphite is used in pencils and you can rub it off with an eraser. Um, like it all boils down to how the atoms are arranged. So that's why it's important, because if you know how they're arranged, you're gonna know how your material is going to behave, therefore know what to use it for. Great. But like how? Like how do you get this information? That's the T. And that's where XRD comes in. XRD stands for X-ray diffraction. Just don't worry, I'll explain what X-ray diffraction really is. But it's basically the technique they use to figure out how atoms are arranged in a structure. But we'll get into that. But first, let's acknowledge the man behind the mystery, Max von Laue. He's the first person that noticed that you could get X-rays diffracted from crystals. And then a few years later, this guy called William Bragg and his son, I think they're both called William Bragg, but they have different middle names. But Bragg and his son, they then won the Nobel Prize because they then devised the method that we all use today for how to like analyze the data you get from the experiment that Max von Laue conducted. Basically, we then have something called Bragg's law. So yeah, now you know it was a father-son duo.
Okay, so this is the infamous Bragg's law. It's n lambda equals 2d sine theta, and off the bat, it might seem intimidating, but don't worry. So let's start from the very beginning. Your material. So over here, this is a plane of atoms, and you basically have an X-ray source that's firing X-rays at your material and like at the atoms. And if you know anything about the atomic structure of anything, like how you'll know that there are electrons outside the nucleus. And so what's happening here is you basically have X-rays coming in and hitting the electrons, and then those electrons are now releasing X-rays. And so then you have a detector on the other side of your X-ray source that's picking up these X-rays. So you have X-rays coming in and X-rays going out. And what your detector basically does is like as it's detecting these x-rays that the atoms are giving off, or that diffracting off the atoms, you end up getting you know I said, you don't know, but you end up getting peaks. These peaks create what we then term a diffraction pattern. And because each material is unique, each material will have a unique diffraction pattern. So if you have, I don't know, a random powder and you're like, oh my gosh, I'm so curious, what is this? And you put it in your X-ray diffractor machine, and you get your data and you plot it, you can compare it to obviously existing diffraction patterns that exist, and compare it, and you'll be like, oh my god, this is concrete, that's so cool. But you go from basically having something unknown to something you do know. Anyways, that's enough of analysis. Back to the Bragg's law. So we have to remember that the X-rays are moving in waves, which helps explain the wavelength function of the equation. And so what you also have is oh yeah, I removed the waves because I don't know, it just means that there's too much going on. So anyways, what happens next is, you if I had drawn this to scale or drawn this how like it actually happens, it should make two right triangles. um if you like, based on these lines here, they should be, just believe what I'm saying.
So based on that belief, like having right angle triangles, we know that triangles have three angles, right? And so if we assume I've drawn this correctly, pretend theta, the angles at the top and the ones at the bottom are equal, right? So if we make that assumption from trigonometry, we can then calculate the length of the lines. So the d aspect of the equation is the space between the atomic planes, so the lattice spacing, and that's equal to this line in the middle. And so from there, like the magic of maths, we can then define the line over here as d sine theta. So the line of the diffracted ray and the line of the x-ray coming in are equal. If you are curious as to why is d sine theta and not cos, I think you should do some math revision. So, um, sorry. And then don't forget, we also have, this wavelength aspect, which is basically the length between one peak and another peak. So if we put all this together and we have our equation back up, it should make a little bit more sense. And n is the order of diffraction, and that's usually like 1 or 2. So yeah, like I hope you see that Bragg was not a fraud. I mean, the Braggs weren't frauds. Yeah. Okay, so I hope that diagram made a bit of sense. But the crux of what I actually wanted to explain is a crystal itself. Like, what is it actually? And the best way that I found to think about it is starting where it all begins. So instead of zooming out from a picture you've never seen, what I found useful is zooming in. Imagine your basic GCSE chemistry, sodium chloride, salt. Your salt is your final form. That's your final crystal structure. You have NaCl, 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 NaCl. If you go down from there and you just take a piece of that salt, you end up with what you call a unit cell. So the smallest bits of just your Na and your Cl, that repeating unit is what you would call your unit cell. And then if you take it down a notch, you end up with just one molecule, which is your Na and your Cl. And then you take one out, and then you just have one atom.
Oh my gosh, I am so tired. Okay, I'm gonna go to sleep now, so that's great because I'm tired. Why would I not be tired when it's so late in the dark time?
You've made it to this point in the video. Good on you. Good on me. Let's keep doing this. It's my bracelet.